So when it goes through space, it goes at a different speed than when it goes through a cup of water, for example. But we're mostly going to we're not going to deal with, there's some slight differences there. They're not going to impact the stuff we're working with heavily, so we're not going to worry about that fact. And we use a constant to represent it. So this is the constant with the speed of light. You will see this sometimes. And it is 3.00 times 10 to the 8 meters per second. Note this will be provided to you on your assessments. So like this is on that equation that I give you on our physics test, if you memorize it, you will see it a lot. What this means is no matter what type of light you're working with, the speed is exactly the same. Note that this is specific to light waves. This is not true with all types of waves. So for example, water waves can travel at different speeds clearly. Sound can travel at different speeds with light. So this is specific to light. The speed has to be a constant. And we're going to use this to look at some other relationships about light. The important part of this means that there are a bunch of different properties that are all connected through the speed. So by knowing one property, we can determine two others. And this helps us out with that. And I'm also going to note that light, if you read your textbook in detail or learned about the subject somewhere else, there's a discussion of the idea that light has properties that both suggest that it has a particle nature and a wave-like nature. For the purpose of this class, we're not going to stress about what that means philosophically. Something can't be a particle and a wave at the same time that it is. And also why we think that the implications that are complex enough that I'm not going to stress about for this class. I do mention that though, but I'm going to talk about light as a wave primarily. It does have some properties that are particle-like, and if you think that is interesting, I'm happy to talk with you about during office hours. This is like my wheelhouse of stuff I did research related to, I think is really cool. But I think that without a lot of math background and a lot of physics background, I just don't think it's as easy to get a meaningful discussion of. So, if I'm going to talk about light as a wave, I need to talk about the parts of a wave so I can talk about those properties. So I'm going to draw something that's meant to represent a wave. We're going to pretend that line is straight and flat. It's pretty close. And so the idea is, when I'm talking about light as a wave, I have to draw it somehow, right? Literal light coming at your eyes is not stationary. It's constantly moving at 3 times 10 to the 8 meters per second. But when you see pictorial representations of light as a wave, it's like you take a snapshot of it. We've also blown it up to be really big because light wavelengths are really, really small. It'd be weird if all the light I saw was so big I could see its wave-like patterns. That would be confusing. So light waves are very, very small in terms of, you can't see this. This is our pictorial representation. So we've got a few points of interest. So waves are going to be periodic in nature in the sense that when you get a high point and it goes to a low, it'll come back to a high. If I had drawn this appropriately symmetrically, this would be as tall from this bottom point here that represents a 0 as this was low. I did not draw it as well, so this looks taller than this. That is not intentional. So the points we can note, if you take any point on a wave and you go to its next point on a corresponding wave, this is called the wavelength. We call this wavelength. We give it the Greek symbol that looks like this for wavelength, lambda. And the idea behind this is that means you take a crest, any point. This is something called a crest. You can go to a node or a trough, any of those points, you go to the next one on the corresponding wave. It has a set length. And the idea is this continues continuously. You'll keep getting these waves to go over and over. There'll be crest after crest after crest if you could draw this really long. Now, the next thing to note is there's one part I can't draw in here, but I can explain what it is. There's something called a frequency. This is our second property we're going to worry about. We abbreviate it with the Greek symbol nu, that looks kind of like a B that's shaped funny. If you just write a B, I'll be fine with it. The idea behind this is something that to talk about requires us to think of this wave as moving. So if I were to take any point on this wave, and I were to have a detector at it, and I let the wave pass for a single second, the number of waves that pass that point is called its frequency. So when I let this wave go, if it takes 1 second for 20 waves to pass the point, I would say its frequency is 20 waves per second. If it was a wave that was shorter in length, so I could get more waves in that second, maybe it would be 40 waves per second. Or maybe it's really, really long waves, so it takes a long time to pass that. So only 1 wave can pass in a second. So a frequency isn't something I can draw in this figure because this figure is stationary. But it represents the idea of the number of waves pass a point in 1 second. I will also note that I said pass a point in 1 second. That's what we'll use for in this class. Technically, you could use any time unit you wanted to, and it would still be a frequency. You could talk about the number of waves that pass in a minute, an hour, a day, a millisecond, anything you wanted. But the unit of a second is useful for all of our equations and constants we're going to work with. So in every case I can think of in this class, I always use per second. But it is not that it's technically a part that would be required. You could do it in some other time component, it just wouldn't be what we would usually do. Now, there's some other parts of this wave I can label. We can talk about the amplitude of a wave. So the amplitude is where I take the 0 point, and the height between this and here is called the amplitude. So that'll be height. And I don't have a variable name for this one. We don't use this one directly in equations. It is a property that will be related to the energy of our wave. Some other things that don't really have points to label in parts of equations, but just to label parts. This point here is called a crest, which is the highest point. Highest, there we go. You can get it a second try. We have a point down here. We call this a trough. That's the lowest point. And then we have points here. We call these nodes. That's where the wave equals 0. So these are points we use to be able to label to talk about a wave. I will admit, I'm not going to use crest, trough, and node a ton, but I want you to know the word enough that I can mention it when discussing something else and it can make sense. But you're not going to have equations where like crest is this value or anything like that. And then finally, the one other variable I have to mention is total energy. We use a big E to represent this, and this just is the amount of energy in the light wave. We'll talk about how to calculate that later. And it is related to both the frequency and the amplitude of your light. It's related to total energy. I'm going to do my best to try to make this as understandable as possible, so I'm skipping some of the deeper explanations for why we understand some of the things we do. But again, I can definitely talk to you about that more if you're interested. I'm going to try to give the minimum amount necessary. So, what we're going to do is we're going to look at what properties can I determine based on information I measure, and then we'll look at what those properties tell us about light, and then eventually about the atom, so in particular, how electrons are positioned in our atom. That's our whole goal with this, is eventually I want to explain why we can shoot light at an atom, and the way that light interacts tells us something about the electrons present there. This is the reason we care about this. So, the first thing we can do is we can go with the fact that frequency and wavelength are related. Now, the reason for this is because of the fact that speed of light is a constant. That means it has to travel so many meters per second. So if you have a longer wave, you can't get as many to travel, it can't have as many pass a point a second because it can only travel at that set speed. So the relationship to the speed of light is that the speed of light is equal to the wavelength times the frequency. And so what that means is if wavelength goes up, then frequency goes down. Or the inverse is also true. If wavelength goes down, then frequency goes up. And both of these are true specifically for light, where we are saying the speed is a constant. If you worked with something where speed was not a constant, this relationship would not have to be true, because then this value could vary, which would allow for one of these to go up, but not necessarily change this one in that way. The way we often describe this is a way of saying that wavelength and frequency are inversely related. Inversely related just means when one thing goes up, the other has to go down. And so this is a property that helps us out because it is often easier to measure the wavelength in the sense of, for example, the color of light you're interacting with. I can tell that from what its wavelength is. And when I know the wavelength, I also have to know the frequency of my light since speed is a constant. Whereas frequency is what I often use in my equations related to energy. So if I know one of these properties, I always know the second, as long as I am working with light at the speed of, which functions at the speed of light. Now, the next thing I want to show you is a picture that you do not have to memorize all the text on this picture. It's just one I have available to give an idea. When I talk about light wave is not just the visible light that you can see. And I don't expect you to memorize this exact wavelength list. The idea is, though, that the electromagnetic spectrum from 400 to 700 nanometers is all the light that you can see visually. Yet light can have wavelengths ranging all the way from 10 to the negative 12 nanometers or even shorter. These are things like gamma rays. All the way up to things like radio waves, if you go as far as like 10 to the 3 meters, they can be things like a mile long. So wavelengths can vary greatly, and the properties of that light change with that wavelength. So what I want you to know is I want you to be able to identify which of these are light waves. I don't expect you to memorize the order that these show up in. Note, I think the textbook does, it may have a few questions about that. I will not directly ask you that on an assessment of which is longer, an ultraviolet ray or an X-ray. Having said that, if you stay in the sciences long term, if you were engaging with this inside of chemistry or physics or certain biological applications, eventually I think you'll get a good feel for this. So the idea is I'd like to know that gamma rays, X-rays, ultraviolet light, visible light, infrared light, microwaves, and radio waves are all types of energy that is light. As opposed to, for example, a sound wave is not a type of light. So a reasonable assessment question would be, here are 4 types of waves. Which of these is not light? And I would want you to identify that a sound wave or a water wave isn't light, but these others are. So that's the extent in which I'd like you to know this. Obviously, more information is never bad. It's if you learn more. And if you take further classes within chemistry and or physics, we'll talk about how particular wavelengths interact with atoms in different ways and give us different properties. But for this course, we're not going to worry about that in great detail. Okay. So, the second thing another thing I'm going to talk about how light works, which is part of how we learn about it, is we want to mention that light waves can interfere with each other. So you need to talk about what that means. So, interference is just the idea that since light is a wave, if 2 light waves interact with each other, they add together. And note, because light can have a positive or negative value, sometimes adding together is like adding a positive and negative value, so adding together can mean getting smaller. Now, when it comes to interference, this topic can get very complicated, but we're going to talk about the simplest case. We're going to talk about when light waves are set up so that they match either perfectly aligned or perfectly disaligned. There are technically a whole bunch of different in-between cases that can give you very complex looking waves. You can also technically add hundreds and hundreds of waves together to make really interesting shapes out of waves. Like I can get things like, it doesn't matter, but the idea is I can take something like a square pulse, you get an electrical wave, and I can put this together with a bunch of different waves, and I can actually build that out of things that look like light. We are not going to stress about that for this course. So I mentioned that because I think it's interesting, and it's a cool thing you learn in physics, or in math class actually deal with it too, the idea of how can I create a bunch of different waves to build something that doesn't look at all like it would be wave-like, and there are neat ways to do that, but we're going to worry about these 2 specific cases. We're going to talk about constructive interference, and so this is the case where I take 2 waves, and Dr. Leslie's going to try to make these look similar. And when I do that, what's important is in constructive interference, the crests and troughs match up. And again, I'm taking the simplest case where both of these lights have the same frequency and wavelength, and so that's going to make these perfectly match up. The answer would get significantly complex when you try to add light of different frequencies, because then sometimes it would line up and sometimes it doesn't. And then it makes more interesting results. But this is the easiest to look at. So when I combine these two, it makes for a new, bigger wave. And it should have the same number of crests. I should be able to continue it off the screen. I didn't give myself enough room. So this adds, make higher crests and lower troughs. Now, you can also do this as destructive interference. In this case, we're going to look when crests of one wave match troughs of another. So in this case, we have a wave, and then our second wave and when this happens, when we add these together, we instead get, they add to cancel each other out. And both of these cases are the most extreme example of how you could do this. If these weren't the same height, aka I can't draw perfectly, so obviously they don't look, these are intended to be, that should be as low as this is high compared to its middle point. But if I didn't match it up just right, then you would get a smaller wave potentially, right? So if you had like one small wave and one big wave and they were mismatched, then you would just get one small wave out of it, because the big wave would lose some of it, but not all of its energy. The point of this is to describe, we use these properties a lot when making measurements inside of science. So there's a lot of different experiments we've done where we've taken different light waves and we run them into each other, and we try to figure out, based on their patterns, do they constructively or destructively interfere, and it tells us something about the properties of that light. So, I will not go on a tangent about cool experiments related to that. I don't want to. I want us to get through these stuff. I will just note, we do neat things where we've got mile-long tubes underground and we shoot light at things, and we need to figure out if gravity exists as a wave. Somebody won the Nobel Prize in 2021, 2022, one of those years. Related to this, I took a class with one of the people that helped develop this, some of the technology to do it, and it's neat because gravity from two colliding black holes will interact at different points on the Earth, slightly different time-wise, so we can see that difference in how far a giant mirror that is bigger than this room moves, and it's kind of neat because you can see, because it makes a different interference pattern, we can figure out that gravity must be a wave. It's called a graviton wave. It's kind of neat. We're still working on it. Okay, that will not be on any assessments. Now, let's do some calculations using the light equation. So we've got through some of the basic concept stuff we want to have. Now let's look at this. So first I want to make a note about units, about frequency. Frequency is in hertz, is what you'll sometimes see it said as. That's hertz. But it can be written multiple ways. So you can see Hz, you can see s to the negative 1, or you can see 1 over s. These are all three the same unit. They're our way of representing the idea of waves per second. And in general, we're saying anything per second can be represented as hertz. In the context of light, we're almost certainly talking on a wave, but in general, a frequency is just something per second. And you'll see it in all three forms, they mean the same thing. So, an example problem would be, calculate the wavelength in nanometers of a laser light emitted from a laser pointer with a frequency of 4.72 times 10 to the 14th inverse seconds. So all of the questions you're going to see about light, you're going to have three variables that are most commonly asked for. We're going to be asked about the wavelength, the frequency, or the energy. And right now we're going to look at wavelength and frequency, then we'll look at how you do it with energy. And if you know any one, you can find the other two. So our equation is the speed of light is equal to frequency times wavelength. And so I want to know the wavelength, so I need to get wavelength by itself. So I divide both sides by frequency. That'll cancel out. I'll be left with the speed of light over the frequency equals wavelength. My speed of light is 3 times 10 to the 8 meters per second. My frequency is 4.72 times 10 to the 14th, 1 over second, since that's what s to the negative 1 is. That's equal to my wavelength. The things that come up here, 1, make sure to check that your units work out. In this problem, it's okay, because this is per second, and that's meters per second. When you're instead given the wavelength, you will often be given in units other than meters, and you have to make sure that they're in the same units to cancel out. So if you use the speed of light in meters, your wavelength would need to be in meters for that part of the problem. In this case, we're going to get the answer in meters and then convert it afterwards. But that's one of the first checks in this section, just make sure your units work out. So here, since I have my units, my seconds are going to cancel, I'll be left with meters, which is the unit I would expect. So I have 3 times 10 to the 8, divided by 4.72, 10 to the 14th. And I accidentally put negative 14, got a really ridiculous answer. There we go. So this would be 6.36 times 10 to the negative 7th meters as a wavelength. Now, this is an answer for what is the wavelength, but it's not the units the problem asked for. It asked for nanometers. So I have to do a second step of now I convert this from meters to nanometers. So I have 6.36 times 10 to the negative 7th meters. And I know that for every meter, I have 10 to the 9th nanometers. My meters will cancel, and I do that, and I'll get 636 nanometers, which note has 3 significant figures, just like my frequency does here. I will note that compared to some other problems you will have done in the conversion chapter, that especially in this chapter compared to all the other chapters in the class, the numbers will sometimes have powers of exponents that can be hard to be sure if your answer is reasonable. And I just pointed out to make sure you're okay with the idea that sometimes you're going to get exponents that are really large, especially for frequencies, and sometimes you're going to get wavelengths that are really small. But depending on the type of light, it doesn't have to be true. So a problem with a radio wave could reasonably have a wavelength of 1,000 meters, which would then also have a very different frequency. But I point this out because I know you can get a comfort feeling for this is a reasonable answer because it's 320 grams, not 3.8 billion, right? So I want to point out that especially in this chapter, you're going to get answers that are very large, sometimes are very small, sometimes, and that is okay. You just have to be comfortable with your units to make sure you're doing your conversions correct. It is not unreasonable to have answers to the 15th power and things like that. So, just to make sure we're okay, I've got one for you to try. Same exact setup, just a different number to go with. Just want to make sure you get the same answer. So I want you to determine the wavelength and X-ray with a frequency of 4.2 times 10 to the 18th hertz. We're going to make sure you get the same answer, and then I'll look at one more example before we do this one. it's from the analysis. It's not what I mean. Okay, I'm going to take a look at this one. One, I was just making sure we can correctly identify variables and figure out how to put them into an equation. So in this one, they gave me one piece of information. They told me the frequency is 4.2 times 10 to the 8th meters per second. I just rewrote it as 1 over second so I can make sure my units cancel. It's fine if you leave it hertz. And then I know that I want to find the wavelength. So when I set this up, I have C equals wavelength times frequency. When I rearrange that, I get C over frequency equals wavelength. From there, I have 3 times 10 to the 8th meters per second divided by the frequency of 4.2 times 10 to the 18th, 1 over seconds. 1 over seconds will cancel. And I've got 2 significant figures here, so I'll have 2 in my answer. So it'll be 7.1 times 10 to the negative 11th meters is my wavelength. This problem didn't specify what unit of length you had to use, so you could leave the answer here. If you convert it into nanometers, that would also be correct. Or micrometers or millimeters or kilometers, all those would be fine. But in terms of the way I think about it is, I just don't want to convert it, it doesn't ask me to. I leave it there.
It's 10 to the negative 11.
Second, I got something else to point out. I forgot to do it.
Just divide it. The minus, so at the bottom is going to be negative because it's on the bottom.
That right the exponent.
Right, so I'm saying 18 is on the bottom, 8 is on the top, so it should be, 11 is the difference, so because the bottom is on the
So
bottom,
one thing I
it should
wanted
be
to
negative.
show was just in case you hadn't seen it, I made an announcement that I made some extra conversion practice problems because I had some people ask me about that. I want to show you where they were. So you go in the content section of the website. Down here I made a new section called extra practice questions. Inside the PDF document here where I've created a set of 14 questions as well as responses to all of them. So if you wanted extra practice with conversions, I have a bunch of problems here. They all have the correct significant figures. This isn't like something with determinant, it's not a requirement, but if you wanted extra practice with conversions, I've written questions here for all the assessments questions, and I have answers so you can refer to them as well. So I realized I didn't announce that at the beginning of class, I just wanted to bring that up. If you find that helpful, that is available in Coursed. For areas where people have a special difficulty to ask me about it, I will try to create a few things. Obviously, it takes some time, so I can't do that for every single section. And the textbook has good practice too, I think. I will try to keep creating additional practice materials as I have time. And then future classes just use them. Okay. So, back to this, I just want to point out that we can do the question the other way as well. Same setup, but let's say we ask for what is the frequency of a light wave with a wavelength of 350 nanometers. So that is my wavelength, and the question's asking me for frequency, so I want to know what frequency is. That's what my actual question is. So go to set this up. I have C equals wavelength times frequency. In this case, I want frequency by itself, so I'm instead going to divide by wavelength. When I do that, those cancel. And the C over wavelength equals frequency. Now, before I go to plug these values in, you'll note that I know the speed of light in meters per second, but the wavelength's in nanometers. So if I just plug these in, my units won't cancel. Technically, I'll get an answer in meters times seconds per nanometer, but that's not a useful unit. It technically is a unit, but it wouldn't answer the question because it wouldn't be giving me a frequency. So I need to start by converting this to meters, or you can convert your speed of light to nanometers. That's also correct, but I find it more natural feeling to convert the wavelength to meters, but neither is more or less correct. So 350 nanometers, every 10 to the 9th nanometers is 1 meter. My nanometers cancel. That'll give me 3.5 times 10 to the negative 7th meters. And then if I plug that into my equation over here, I have 3 times 10 to the 8th meters per second divided by 3.5 times 10 to the negative 7th meters. And that'll give me 8.6 times 10 to the 14th 1 over seconds, or hertz, or s negative 1, those would all be fine. And then again, I used 2 significant figures because there were 2 in my problem. It was 350 nanometers. There's no decimal place, so my 0 at the end doesn't count. So that's why I only had 2 significant figures. And this is just to show the idea that you can calculate this for both frequency and wave. Okay. Note that if you were following along, like if you go back and look at the notes online, I have 2 slides about standing waves, and I realize they just don't come up anywhere else, so I'm not going to worry about them. What I want to talk about now is our third problem. So instead we can talk about wavelength and frequency. These 2 we are usually interested in because of their relationship to energy. So wavelength and frequency are easier to measure, but I'm usually more interested in energy as a chemist, as this is what's going to tell me, yes?
Are you looking at me?
Okay.
So why did you say that we have to convert it to meters first again?
Gotcha. So the reason I did that is because if I put this in nanometers, these are different units, so they wouldn't cancel out. So it's like when you put them into an equation, so I would have meters divided by nanometers as part of my unit. And so I eventually want to get just seconds by itself. It's kind of like all our conversion problems here. We're trying to keep it in the right units. So yeah, so if we put meters here and nanometers here, then that wouldn't cancel.
All right, thank you.
You're welcome. And thank you to the person who helped to highlight that for me. Okay. So what I want to look at now is we've got our 2 units, we've got frequency and wavelength. Both are connected to energy. The reason we're interested in this is your atoms are going to be able to gain or lose energy. To measure that, we're usually going to measure light that either the electrons absorb in the atom, or that the electrons release in the form of light. So by measuring the wavelength or frequency of light, I'm able to learn about how much energy my atom gained or lost. So this is the connection to chemistry rather than just, hey, light does this thing, you have to learn it. There is a reason that we're carrying about this. So what is the relationship between energy and both of these? We have 2 equations. Energy is equal to Planck's constant times frequency. So this is energy. This is a constant that if you study things that are small, like light, and we talk about electrons and stuff like that, you'll see a lot. It's called Planck's constant. This will be provided to you. But we will use 6.626 times 10 to the negative 34th joules times seconds. And that's our frequency that we've seen before. So this relationship means anytime you know the frequency, you also know the energy of a light. Now, this energy, we're also going to state this is the energy of 1 photon of light. So I have to say, what do I mean when I say photon of light? So photons are the smallest possible packet of light. So what I mean by this is energy is something that when we talk about in a macroscopic sense, I tend to think of it as a continuous variable. It can have any value I want. I can have 1 joules, or 1.5, or 2, or 10, or 16, or 16.2394669. Whatever I want, I can have any number I want. This isn't true, we found, for the amount of energy that light can carry. Light, while it has wave-like properties, that light can only have very specific amounts of energy. This actually has a tremendous number of applications. It was one of the most difficult problems in physics for a very long time. People won a Nobel Prize related to this process. But the details of how you figure this out are relatively complex. So we're just going to go with this is a statement. This is something science has worked on for a very long time and are very confident is probably true. I make the statement probably true because technically everything could be not true, right? We could find out tomorrow that gravity doesn't actually work because gravity only works to some time point and I fly off the planet, but I am not nervous that gravity is going to stop functioning tomorrow. I've never woken up and had worries about that. Similarly here, I am not worried that we're suddenly going to decide light doesn't come in photons. But I mentioned that technically. something that we have very good evidence for, but if someone can do a good enough experiment to disprove it, that is always possible. So this is the energy for one photon of light. So we will talk about both. Sometimes we'll talk about single photons, because this is related to how much energy a single atom lost. So we can learn something about the property of light, of how much does a single atom lose when its electron changes its position. And that can give us information. In other cases, I'll be interested in when we've got lots and lots of light together, and then I might talk about energy per mole of photons, and I'll get much, much bigger numbers. Both have different circumstances where they're useful. If I want to use light to do a chemical reaction, so it's part of the chemical reaction process, I'm going to probably talk about energy per mole of photons, because I need a whole bunch of them. In other cases, I want to know how much energy does a single hydrogen atom change when it gets excited and it gains energy, then I'll talk about a single photon. This equation is specifically the energy for a single photon. So if I want to know the energy of a mole of photons, it would be whatever number I got here times 6.022 times 10 to the 23rd. So this is the energy for one photon. We can also do this same equation, the energy of one photon with wavelength. That's equal to Planck's constant times the speed of light divided by wavelength. You can also do it there. So in this case, I don't have to change wavelength into frequency first and use this equation. I can also use this one. So whichever variable you know, you can use that. So these equations are all related. You could use the other equation that converts wavelength into frequency first and plug it into the top equation, you'll get the same answer. If you're observing, you'll notice that's really what we did here, right? We took frequency. Frequency is equal to C over wavelength, so we just plugged it in there. That was the idea. So,
Energy.
and note this means the energy of a photon of light is a specific amount, so you can't have the energy of half a photon. You can't have the energy of 1 1/3 photons. It has to be an integer number.
Ask a question.
So this is because light travels in these particular paths. So what does this look like? So I can say things like,
Energy of one photon.
what
Is this one?
is wavelength of a photon with an energy of 6.52 times 10 to the negative 19 joules. In this case, my question asks for wavelength and gives me energy. So I can use my relationship between the two, which is E equals hc over wavelength. Remember, h and c are both constants that have set values. This here is the energy, and this is the wavelength that we're looking for. So I need to rearrange this equation. Here, wavelength is in the denominator, and it's not by itself. Because I want to solve for it, I need to get it by itself. So I'm going to take two steps. One, I want to get it out of the denominator of my fraction. I want it to be up top. So I'm going to multiply both sides by wavelength. Multiply wavelength times wavelength. I like my black. Should go better. When I do that, these will cancel, and I'll be left with wavelength times E equals hc. Then I'll divide both sides by E. So I get wavelength by itself. Those will cancel, and I'll be left with wavelength equals hc over E. Now, I will note, when you are very comfortable with your algebra, it is possible to simply look at the top equation and get this bottom equation by doing some rearranging. Make sure you're very comfortable if you do that without doing explicit steps. The most common errors I see students do is they don't realize what things are going to go to the numerator and denominator in different contexts, and end up putting things in the wrong place. So end up with things like E over HC. So make sure that you're very explicit about it when you're learning until you get incredibly comfortable with moving these things. And if you already are from algebra class, I am fine if you just go straight from here to here and don't show me these in-between steps. But I'm going to continue to do them because I think it's good practice to get practice. Okay, how do I make sure I'm putting the variables in the right places? So now, we have these. They're also in units or energy is in joules. Planck's constant is joules times seconds. So these joules are the units for both, and so joules are going to cancel out. Planck's constant also includes seconds. Our speed of light includes meters per second. So that's going to make the seconds cancel out. And then we'll be left with only meters, which is a unit of length, which matches up for weight. So this is 6.626 times 10 to the negative 34th joules times seconds. The speed of light is 3 times 10 to the 8th meters per second. Reminder, these are both constants. They're both given to you on your useful information sheet you have in front of your quizzes and you'll have on your test. And then the energy was given to us in the problem. It was 6.52 times 10 to the negative 19th joules. So our joules will cancel. Here, seconds is in the numerator, it's in the denominator here. That'll cancel. We'll be left with meters. So, we got two things to multiply together. We want to divide by. When I do this, I get 3.05 times 10 to the negative 7th meters. And again, this problem didn't specify the length unit to use, so meters is fine. If it had said nanometers, you would want to be able to convert that from something else. So, most of these questions about energy, wavelength, and frequency will come down to being able to identify which of the three equations you have to use, correctly identify your variables so you can plug them in right, and do the algebra right with rearrangement. An extra little step is you do have to make sure your units work out. Now I've got one for you to try. So instead, I want to know what is the frequency of a photon that has an energy of 3.43 times 10 to the negative 16 joules. So the wavelength, what is the frequency? Okay. So with this, it's about identifying the thing we're given is energy, and we're asked for a frequency. So, what that means then is that I need to use my equation. Energy is equal to Planck's constant times frequency. When I rearrange that, I'll get energy divided by Planck's constant is equal to frequency. So I have 2.43 times 10 to the negative 16th joules divided by Planck's constant, which is 6.626 times 10 to the negative 34th, joules times seconds. My joules will cancel, and this will be 1 divided by seconds, which whatever seconds is a frequency unit, and I'll get 3.67 times 10 to the 17th inverse seconds, or 1 over seconds, or hertz. All three mean the same thing. And I have 3 significant figures since I had 3 of my energy that I was given. So So this is just these two equations. Most of the practice will be, I think when you're told directly, you just learned it. It's not too bad. You have to use this equation, just making sure you can keep this in mind when we learn about other additional information as well. So I have two more big ideas I want to make sure I get through to get you to workshop, and then I'll make sure to practice themselves. So all of this has been because we want to talk about the energy of a photon because it's related to how atoms release or gain energy. So I want to talk about a concept we call an atomic spectrum. So an atomic spectrum is just the set of wavelengths of light unique to the absorption pattern for any atom or molecule, for an atom or molecule. So the idea behind this is when I want to learn something about an atom, I can hit it with light, and it won't just absorb any particular light. So if you took the light from this room that is broad spectrum white light, that's fluorescent light, it's not broad spectrum.
Right.
If you took sunlight, it includes all the different wavelengths, and if it interacts with a particular atom, it's only going to absorb certain ones of those. And so what I can do is I can use an instrument that will bombard a particular sample with set wavelengths of light, and I can see which wavelengths get absorbed and which don't. It's called an absorption spectrum, and based on what atom or molecule is present in my sample, it's going to show up in different ways. So I have two examples that I'll show here. So down below, these are two different spectrums. This top one is what happens if you have hydrogen by itself. At least in the visible spectrum, hydrogen by itself absorbs 4 different wavelengths of light that are like a violet, indigo, something in the cyan blue section, and something that's red. These have very specific wavelengths associated with them, and you can go back and calculate, based on the wavelengths of light that hydrogen absorbs, how much energy is absorbing when that happens. And we're going to look at next in a little bit, okay, so how does that energy relate to the structure of hydrogen? Then as atoms get more complicated, you'll sometimes see a lot more emission spectrum, or a lot more absorption. So down here, this is the spectrum for iron. Iron has hundreds of different wavelengths of light it can absorb. This is related to the fact that iron has a lot more electrons in it, and so, or even it's mostly the highest energy electrons. So some of the electrons aren't interacting with light waves in the visible spectrums, but the ones that are in iron can interact in a lot of different ways, whereas hydrogen only has one electron that has fewer possible interactions with it. And so these spectrums look different. Now when I look at it here like this, it's hard to imagine, okay, this is a fingerprint that I can tell this is exactly iron. If you do these calculations well enough, we've measured them well, we have giant libraries of literally hundreds of thousands of molecules, way more than thousands of molecules. Very large numbers, and ones for all of the different atoms. And the idea is that if you know all the different wavelengths and their intensities, you can get an idea of which species it should be. This is actually how we learn most of the material we learn about space. As you might imagine, if I want to know about chemistry about a star, especially one that's not the sun, I can't just send a satellite out and pick a cup of the star up and look at the chemistry, right? I can't get to it. Even with the sun, I can't do that because if I try to send a satellite there, it's just going to melt, right? So I have to make inferences based on what I can see. And the thing I can see out in space is light that's coming out. And so I can figure out, based on properties, what I would expect, what the chemistry inside of, for example, the sun is happening based on the different wavelengths of light it's giving off. And that gives me ideas of what's happening. This is the area where we're especially interested as people who do astrochemistry, because light is almost the only way to learn anything about space. Technically, that's why the discovery of a graviton wave is interesting. It's a way to learn about things like black holes that don't emit light, so it's another way to learn about it. But almost everything we know about space is based on the light that comes at us. And so we can use that to help figure out what's happening. Now, related to this, I've got a specific equation I want to make sure I get to, so that it'll help your class, but we will get there. So, related to this, we're going to talk about the Bohr model of the atom, which helps explain why these specific wavelengths come out. I want to note, the Bohr model of the atom is imperfect. There are some assumptions it makes that aren't quite true. But it does a great job at demonstrating this idea, so we still teach it, because the parts that are wrong don't change the things that we see. So, and it's still a pretty good idea, even when you learn some details about why it's not quite right. But the idea behind this, and the big discovery that Bohr had, was Bohr realized that energy of an atom was quantized. So what does that mean? So quantization is related to that idea where I mentioned it's kind of like how photons can only have so much energy. In an atom, when we're looking at the electrons in it, they can only have set values of energy. So a hydrogen atom with an electron in it, that electron can be in different positions, but it can't be in any position at once. It has to take set values that we call energy levels. The idea that it takes these set values creates what we call a quantization effect. It means it can only have specific values. This has a bunch of important implications, but practically it means we see only specific amounts of energy. The electron can gain or lose, which match up with what wavelengths of light that atom absorbs. So hydrogen is the simplest case. There's only one electron. That one electron, because it can't take any particular position, when it gets hit with a photon of light that is an amount of energy that wouldn't let the electron transfer to a specific energy level, it just doesn't absorb it because there's nowhere for that energy to go. It can only absorb photons of light that have the right amount of energy for that electron to move from one energy level to another. So, because of this quantization, Bohr's model has electrons travel in orbits that are a fixed distance from the nucleus. And this fixed distance would be related to the amount of energy. I will make a note here. This statement is not quite true, but it works well for our approximations. The issue is that electrons actually have wave-like properties just like light does, so they can have particular energies, but they're not in like a single spot. Having said that, this model worked well when Bohr discovered it because we were still getting the idea that an electron could be something other than a particle. It's weird, the idea of what does it mean that an electron's a wave, and it still works well for explaining why this distance is here, because it's still true that the electron waves can only have specific energies. It's just the explanation is a bit off, but this will work well enough for this. So, in his model, when electrons enter new orbits, they emit or absorb energy based on the distance traveled. The idea behind this is each position, each orbit represents a specific amount of energy. So if you take the difference between two orbitals, two different positions that electron could be in, and you look at that difference, that energy will match up with the photons that are either absorbed when it's gaining energy or released when it's losing energy. And because of this, we can use that as an explanation for why certain atoms have certain fingerprints of which electrons are added or removed. So, got a picture here from your text of the model as it relates to hydrogen. So hydrogen, we have these energy levels. This N we'll talk about next class. It's called the principal energy level, but it has with how much energy you can have. And so these represent the first 6 energy levels of hydrogen. And so specifically, if you take an electron in the 6th energy level, and you take it to energy level 2, that matches up with a 410 nanometer wavelength light. So if you can actually get values for these energy levels, subtract them from each other, and then you get an E value, and you plug it into that equation, E equals h over wavelength, and you end up with 410 nanometers. We'll actually do this in just a moment. The same thing with like 5 to 2 is 434, 4 to 2 is 486, and then 3 to 2 is 657. Note, they're not going to n equals 1, not because that's impossible, but because that produces light that's not in the visible spectrum. That produces UV. That's just because it's a different energy level. One thing about this picture that's a little off is the distances between these 1, 2, 3, 4, 5, and 6 is not equal. As you get higher and higher, they get closer and closer together. So for a more accurate picture, I like this picture because it shows the eddy distance, but 1 and 2 are much further apart than 2 and 3, which are much further apart than 3 and 4, and it gets closer and closer together as you go up to n equals 6. And technically this can go out infinitely far, but as you get much above 6, you get like 7 or 8, they get so close together that they almost merge into one thing. And so eventually, if your electron gets too far away, it moves you out. So that's how it would be formed ions, that's how electrons leave, is eventually, this nucleus is positively charged. You get this electron far enough away, and the electron's like, I can't even tell there's a nucleus there anymore. It just flies away. So that's why I don't tend to go to like n equals 100 or something, because as it gets further and further away, it's easier to just get enough energy to leave the atom. So, but this matches up with these particular colors. And as you might imagine, if there were more electrons, it wasn't just this one, you would have multiple electrons that could change the energy levels, and that would give you more possible answers. On top of this, once you get to more than one electron, these energy levels get more complicated because they're going to have different sublevels in them. We'll learn about those in a class or two. But for a one-electron system, each of these n values only has one possible energy. You start to get some separation once you have multiple electrons because they interact with each other and cause there to be lots more possible energies. But hydrogen is nice because it helps us for simulating these things. Okay. So, 4.8. So, what we're seeing is when an electron absorbs energy, it becomes excited. This is the word we'll use for it. That's a vocab word. And transitions from a low to a higher energy, from a lower energy level to a higher energy level. So in most instances, electrons start in something we call the ground state, where they have as little energy as possible, and they're happy that they don't want to have their electron further away than is necessary, so they have as close as possible to the nucleus. If the electron absorbs some energy, it will temporarily become excited. It will now be in a higher energy state. That energy state isn't stable. So, the electron tends not to stay in this excited state. Note, I say tends to. One problem with this chapter is every single statement I make, compared to other chapters even, has a bunch of qualifiers. I'm making a bunch of approximations and not worrying about corner cases. Like, for example, I can excite an electron in very specific ways. It causes the electron to want to stay excited. For example, that's why the little, have you ever seen the stars in someone's room, like, that light up, that stay lit up after you turn up light? Those come from certain types of atoms. If I excite them, I can put their energy in a level where it can't get out easily, and then it very slowly relaxes down over hours or days. That's what makes those stars glow, is you excite them with light initially, but you excite them in a way they get stuck and can't get out, and they very, very slowly release. In almost all other cases, other than neat little stars and other things like that, this process happens in under a nanosecond. It happens even faster than that, so it's very, very quick. The atom gets excited, it goes, whoa, I don't want to be excited, this is more energy than I need to give it away. And so, when that happens, the electron relaxes. This is our other word, we've got excited or relaxes to leave the excited state. And releases a photon of light. The reason for this is when it gained energy, it did that because it got hit by light and it absorbed that energy. The energy can't just disappear. So one of the ways we can look at this is it can relax by letting the light leave. So it gives off a photon. Note, this is not the only way an electron can lose energy. You can also do things like vibrational systems can make it lose energy. But this will work for most of the things we're looking at. Now, Your textbook has a good pictorial representation of this. So, this is your textbook. Idea is, electron starts down here at n equals 1 in the case of hydrogen, and to start, it's going to be at exactly one place. It's then going to absorb energy to enter a higher energy level, and this distance, as it gets larger, is going to have a larger amount of energy, which means it will, because it's a higher energy, it'll be a higher frequency photon. And remember we said that wavelength and frequency are inversely related, so as you get the higher frequency photons, that means they're going to be smaller wavelengths. So as you get further and further away, it takes more energy, so you get a shorter wavelength.
Wait, but isn't red the longest wavelength?
This was not the greatest color scheme they created for this. Because that is not a good matching of that. Because with this, because you're starting at n equals 1, none of these energy levels would be visible, so they just picked a color scheme to go with. But yes, you are right. Red is lower energy, blue is higher energy. I would have preferred they reverse these as well. But yes. And also note that when it gains, it doesn't have to lose in a single point. So for example, it shows here, you could be at n equals 5 and go to 2 first, and then go from 2 to 1. So you could, in theory, lose 2 photons of light, rather than 1, because if you take a hydrogen atom and haven't done anything to it, almost all electrons are going to be in this n equals 1 state. Then when you excite it, though, it doesn't necessarily have to go straight from where you excited back down. It can go from somewhere else. You can also, in theory, excite an atom by giving it 2 photons of light. First, you go n equals 1 to 2. While it's still there, you can hit it with a different light beam and take it from 2 to 4 or something like that. These transitions, it's just important to note, when they absorb light, they go up in energy level. When they release light, they go down in energy level. We call that absorption process excitation. We call the release process relaxation. So those are the important parts to note with this. And yes, and this is a better representation of the idea that 1 is really far away from 2, and then 2 is far away from 3, and then they get pretty close together. And the last line is supposed to represent infinity of that's just, eventually the atom gets away, or the electron gets away, and it just goes, hey, I'm going to go somewhere else. Because you gave me so much energy that I don't even notice there's a nucleus to interact with. So the equation I wanted to make sure I got to because it's important for your homework. So that representation of the idea that light can go from particular n values has an equation version we can use to represent it. This is something called the Rydberg's equation. I don't care that you know the name of it, but what we'll do is we'll do the equation form of absorption / emission. So that's when it absorbs the light. This is when it gives it off. The equation works for both. So 1 over wavelength equals a constant called R. This is the Rydberg's constant, times 1 over the energy level that it gets to in the end, that's NF, squared, minus 1 over the starting n value squared. Note, this R is equal to 1.097 times 10 to the negative 2 inverse nanometers in the case of hydrogen, which is what we're going to work with. So, I will admit, this equation is written, has some limited uses. We mostly want to conceptually show you this is how we make this calculation. This equation only works for atoms or ions that have exactly 1 electron. So this is the equation for hydrogen, helium plus, lithium 2 plus, beryllium 3 plus. Those systems don't exist naturally very easily. We mention this because it is useful for being able to calculate things exactly. For reasons we're not going to worry about in this class, as soon as you have 2 or more electrons, you get some very strange behaviors that are hard to model and talk about because they don't match up with what happens with large macro scale structures. There are parts of our equations related to something we call exchange energy that do not have a counterpart that we can explain in a way that makes any sense. Which is a version of saying, we know the math works and we get the right answer every time, but explaining it at a macroscopic level doesn't really make sense, but it works for things that you can't see that are microscopic, so that's why we're going to stick to the 1 electron system. But every time we talk about the shape of an electron, we find that it does all kinds of cool things in multi-electron system we can't prove it.
What is N again?
N is the energy level. Yeah, so So this, and NF represents the final energy level, that's where you're gonna get to.
Initial.
NI represents the initial energy level. Note, there's also a second equation we can use, that the change in energy is equal to K. This is just another constant. In this case, K equals 2.179 times 10 to the negative 18 joules for hydrogen times 1 over N1 squared minus 1 over N2 squared. Note, I grabbed these from two different places. I don't know why one person uses 1 and 2 and one uses F and I. I could have just done F and I. That being F, that being I. Note, with the energy difference also, your photon can't have negative energy. If you get an answer that says negative, I'm fine if you tell me the photon itself has positive energy. The reason you will sometimes get negative values if you're talking about something losing a photon, the system is losing that energy and it's going in the place of a photon. So the energy of the photon itself is positive, but the system lost that energy. So something does not have, so a photon doesn't have negative energy, but you can talk about a system losing energy. Yes?
Is that underneath the second end?
This one?
Yeah.
That's a 3 2.
Okay.
So yeah, it's just the first wavelength of the second, or the first energy level of the second energy level.
Would that be an uppercase or lowercase?
It would be a lowercase k. I just was really bad at writing things. That should have been lowercase, yes. Nope, I'm going to show one example real quick. I'll make sure I got to at least one for class ends. So we're going to determine the wavelength of light. Wavelength of light with an electron in a hydrogen atom transitions from n equals 5 to n equals 3. I want to note, just so like when you get to homework problems and stuff, sometimes we add some extra words around here. Mostly it's because we're trying to be technically correct about things. Like honestly, it matters that it's a hydrogen atom transition because this equation doesn't work otherwise. But I'm not going to give you an equation other than hydrogen because you can't solve it, you don't know how. So I mentioned that sometimes we're a little wordy in these problems in general in the light section because we're trying to be technically correct for like if someone who knew a lot of physics or chemistry saw it. In many cases you're going to look at, why did you add all those extra words? It's because we're trying to clarify there's a whole bunch of assumptions we're making. So if we go to our equation, we have 1 over wavelength equals 1.097 times 10 to the negative second inverse nanometers times 1 over, our final n is going to be 3, so it'll be 3 squared, and our later n is going to be 5, so it'll be over 5 squared. Okay, so we have 1/3, or 1/9 minus 1/25. Give me the fraction. This is 16 over 225, 4.0711. Note that for this one, I'm not going to count for significant figures because the problem doesn't give you anything. These are absolute counting numbers. They've been significant figures. So you can give me an answer with like 8 significant or 3 or 4. Just give me more than one. So don't like round something to like 800 or something. But for this, I don't have a specific number of things you have to give because that would make sense in this problem. So I have 1 over wavelength equals 1.097 times 10 to the negative second inverse nanometers times 16 over 225. I can then multiply those together. And then that will be a decimal. So I have 1 over wavelength equals 7.801 times 10 to the negative 4th inverse nanometers. Note, this is not the answer for wavelength. This is 1 over wavelength. So if I rearrange this, I'll get 1 divided by 7.801 times 10 to the negative 4th inverse nanometers equals wavelength. When I do that, I will get 1,280 nanometers equals my wavelength. Note, since I did 1 over inverse nanometers is 1 over nanometers. I've got a complex fraction, so that's 1 divided by 1 over nanometers. Remember your complex fractions right. You invert this when you move it, so it's 1 times nanometers over 1. So that's just nanometers. And then 1 divided by this number gives me 12. So where we're at is this gives us some of the information about how we're making calculations about things related to energy. Where we're going to move on next class is we're going to start talking about how we represent that as information we call quantum numbers, and how we deal with this in multi-electron systems. That's what we're moving on to here. So we should have workshop on Wednesday, and Monday we will look at this as well. Monday. See you next week.